Okay, so it's time. So let us start. So welcome everyone to this first question and answer session for LICS. So we have an interesting program ahead of us. And so the first speaker is Jim de Groot. And the paper is Modal Intuitionistic Logics as Dialgebraic Logics. So do you want to share some slides?
Yeah, please.
I mean, you have a share screen option at the bottom.
So I think you have to stop sharing before I can start sharing.
I'm not okay.
The problem is that we are going live in a few seconds, so
okay.
just
okay.
let us wait.
Yeah.
I don't know, 20 seconds or like it's just turning.
Sorry.
It's working. A few seconds.
No rush. All good.
Yes, so now we are live. I stop screen sharing now and you can start.
Yes.
Okay, so can you share now?
I'm trying to. Okay, so if all is well, you should see modal intuitionistic logics as dialgebraic logics now.
For now, we see your camera.
Oh, huh?
I see your slides.
You are sharing screen, it says.
I can see your slides right now.
Okay.
Me too.
Okay, how do I'm not seeing them for some reason.
I think there are two screens. One is with the video on the face and one on the slides, right?
There's not much on the slides, so you're not going to miss anything.
Okay. So let's not lose too much time on that. It's not a big deal if I don't see the slides. So so Jim de Groot, Modal Intuitionistic Logics as Dialgebraic Logics.
Thank you. So this is joint work with Dirk Pattinson, and I'll tell in 1 minute, hopefully, more or less what we did. So the main idea is as follows. Co-algebraic logic is often used as a framework for, as a semantics for modal logics in all sorts and varieties. But for intuitionistic modal logics, often this co-algebraic framework does not work. And what we do in the paper is extend co-algebras slightly to dialgebras or specific version of dialgebras. And then not in all cases yet, but we capture a variety of modal intuitionistic logics. So this is more or less the content. And what we get from this is generic weak completeness results, and a notion of prime filter extensions and when these things exist, and similar notion of expressivity and when things are expressive or expressive somewhere else, and generic results for this. But there's a whole bunch of questions that we still have. So this is more sort of the start of a research line than the conclusion. So a very prominent one is how we can cover modal intuitionistic logics that are famous, like the ones by Simpson and Fisher-Servi in our framework. So we cover ones by Walter Zakayashev and Bosi Todosian and a bunch of others, but definitely not all modal intuitionistic logics fit the framework yet. So this is work in progress. And then another question that we're looking at right now is can we use the framework that we set up in the paper or in the video for other logical paradigms or like other base logics? So it seems suitable not just for intuitionistic logic, but there should be more in this. And that's what we are investigating at the moment. That's all.
Okay, thank you very much for this nice presentation. So are there any questions? If you have questions, then I suggest you can just unmute and ask the questions. Let's keep things simple. Okay. If there are no questions, then I can ask a slightly naive question, which is, so what is the difficulty, for instance, in handling Simpson's model logic? You're mentioning that as further work.
Yeah. So the difficulty is that when we extend intuitionistic logic with modal operators in this framework that we're using, then the axioms that our modal operators satisfy cannot involve the implication. And in many examples, this is the case. So it's only, for example, boxes distribute over meets, and that's all. And the reason for this is that the implication is more or less interpreted as a modality as well, but in a subtle way. So then if you have axioms that connect boxes and diamonds via this implication, then this behaves like a sort of an axiom of depth 2 instead of, or of rank 2 instead of rank 1. And in co-algebraic logic and in our setting as well, the rank 1 axioms are the ones that we can handle, and rank 2 seems too much. So this is what makes it hard for example, for Simpson's IK.
If there are, I can ask another question, but are there questions in the room?
I have a question. I can wait for you, or I can ask now.
No, go ahead.
Okay, so you note that the framework can it be useful for other logical paradigms? I guess you mean other logics. Is that right?
Yeah.
And do you have any thoughts on where this might be used or where it could be useful?
Yeah. So I have a few examples that are like slight modifications of intuitionistic logic. So for example, by intuitionistic logic, or modal extensions of this, or fragments of intuitionistic logic. So an example of this is the meet implication fragment of intuitionistic logic. You can consider and then add modal operators using dialgebras. But these are all sort of very closely related. But I've had suggestions to look at relevance logic in sort of Routley-Meyer semantics, but I haven't understood this enough yet to see if this interacts. But the framework allows for much more general things than, it's not tailored for intuitionistic logic, is what I'm trying to say.
Okay, I can have a follow-up question if you can.
Yes,
let me.
please.
So in the cases where it can be used, do you think can you see some metalogical results about the logic that we could prove using this method?
So far for results, we've focused on this completeness and prime filter extensions. That's where we get general results, and these let me think. So the completeness we sort of re-obtained from known examples like Goldblatt's intuitionistic logic with a geometric modality, or conditional intuitionistic logic. We re-obtain weak completeness. But for example, the prime filter extensions in these cases would be a consequence of our framework. You could, of course, prove these things separately also, but they also follow from the framework, and they seem to be new somewhat.
Sure.
Okay, we have time for one other question, if there is one. If not, then perhaps we can go to the next paper. So thanks very much for your answers.
Thanks for the questions.
So the next speaker is Thomas Erard. Thomas, are you around?
You are muted.
Thomas, we cannot hear you. Your
Okay,
microphone
yes,
is
it's
muted.
good. Can you see my slides?
Yeah, we can see you now.
Okay, so
Yes.
okay, so it's a paper about semantics of probabilistic programming languages, where one interpret types as some kind of spaces of probability distributions and generalization, and programs as very regular functions between these spaces, which can be seen as probability distribution transformers. So the objects we consider are two kinds in the paper. First, probabilistic coherent spaces that we introduced many years ago, actually now, which are concrete combinatorial objects, and abstract. The other objects we consider are abstract objects, which we call positive cones, which appear actually which have appeared. This kind of objects have appeared many years ago in the theory of Banach spaces, and they can be seen as some kind of vector spaces with non-negative real coefficients. And so the main feature of these objects is that PCSs, they provide a model of classical linear logic. Cones give rise to a Cartesian closed category where we can interpret probabilistic extensions of PCF which contained continuous data types such as real lines or a product of real line. And the result of the paper is that first I proved that probabilistic coherent spaces are dense in cones. Any cone is a co-limit of PCSs. And then define a tensor product on cones, which we didn't have before. And for this, we use the spatial adjoint functor theorem using the good properties of the lollipop functor. And then I proved that the tensor is associative using the density property, which was the first property I mentioned. And this shows that cones are a model of intuitionistic linear logic. And this opens the way to defining models of call by value lambda calculi, in this kind of denotation setting where programs are interpreted by analytic functions. And another nice thing, I think, is that this is an illustration that categorical methods can be very efficient for building objects. So thank you very much. That's what I mean. Summary.
Thank you very much. So any questions in the room? If there are no questions, I'll start myself with a question. So you mentioned in the talk that you have, so you use this categorical construction to build the tensor of cones. And you mentioned in the talk that you have a candidate for a concrete construction of the tensor, but you were not able to prove directly that it has the right properties. So I guess there are two questions then. What makes it so difficult to prove that? And the second question is, I suppose you expect the construction you get through the categorical mechanism to coincide with the concrete one. Is it something that you can show, or like a posteriori show that the concrete construction is okay?
Yes, to the second question, the answer is yes. Yes, a posteriori, you can prove that the categorical construction gives what you expect at the beginning. And the difficulty to get it directly is that, contrary to vector spaces, it's not completely clear how to perform quotients in codes. And we define a tensor product, you have to take a quotient. That's the main technical difficulty. So when you want to try to do it in codes, you have to iterate some kind of completions and quotient, and that's not easy to understand what you get at the end.
I see. Okay. Questions? Other questions from the room?
I have a question, but maybe other people have a question too.
Wow.
I can ask mine. So
go ahead.
Yes. So you show that the category of coherent spaces, probabilistic coherent spaces, is dense. Yes. And so that means that there is a functor from your category of cones to the category of presheaves over coherent space. So I'm wondering, can you can you see what kind of like sheaf property or something like this you could use to reconstruct your codes from the as presheafs or specific presheafs of your probabilistic coherent spaces?
Yes, that's a very natural question, but I really that's really something we have to address, but I really don't know how to do that. But that's a very natural question. Somehow to characterize the image of these
Yes.
full and faithful functors from cones to presheaves. One thing which is funny is that actually when I say that cones are dense PCSs are dense in cones. Actually, you have a category with only one object, which is already a subcategory of PCSs with only one object. It is a monoid, which is already dense in cones. So maybe one has to restrict to this object and try to find some kind of topology to define.
And so what does it look like? This.
Well, it's just the orthogonal of natural numbers. So it's it's a kind of L infinity, if you want.
Okay, so the object is already enough to distinguish the various apps.
Yes. Yeah.
Okay, interesting.
Other questions? So I have another question. You said that this could be helpful in modeling call by value languages in cones. Can you elaborate on that?
Yes, the idea is to use translation of linear logic. Lambda call by value lambda calculus in linear logic. The good old
yes
construction by Girard and then Wilder and so on. And the difficulty here is that essentially one has to define one has to interpret a sampling operation, and this requires to define to have a theory of integration of functions valued in cones. And so there is a little problem here. So maybe, but I think that well, there are work in particular by Sergei Slavnov, which could be useful in this in understanding what has to be done here. There is still a technical problem.
Okay, thank you. We have time for one or two more questions. So I can ask one last question. So this builds a silly category structure on cones. And the question is, so there is also the silly category structure on probabilistic coherent spaces. So do those agree with each other?
That's not completely clear. Actually, I'm not sure. I could prove that the tensor of cones is just an extension of the tensor of PCSs. But for the exponential, it's not completely clear how to do that exactly. So it's still an open question. I'm pretty sure that it's a case and that it should be a consequence of the theorem by Raphaël Kripke that the CCC of cones is a full subcut of the CCC.
Yes,
no, CCC of PCS is a full subcut of the CCC of cones.
Yes.
But I don't know exactly how to do that.
It would be very surprising if it wasn't the case. There would be something
fishy
going on.
Yes, in view of this result, it's clear that it should be the case, but there are some technical issues there.
Okay, thanks very much for the answers. I think now could be a good time to jump to the next speaker. So
thank you. I have to ensure like this. Okay.
So the next speaker is Leo Stefanesco. I think will be talking.
Okay.
Okay, and the talk is about concurrent separation logic meets template games. So please go.
Okay. Yeah, so it's a joint work with Paul-André, who is also here. So first I will explain what is concurrent separation logic. So it's a program logic for concurrent programs with shared memory and LOCs. and as an extension of our logic. So it's based on 4 triples with a precondition P, a postcondition Q, which proves the program C. And there are inference rules, which lets the prover build derivation trees with a 4 triple as a conclusion. And the general approach that we use is that basically we interpret both the proof pi of some 4 triple and the program C itself as 2 objects. So here's the interpretation of the proof and of the program, which live in 2 double categories, which are induced by what we call templates. So here's one template for the proofs and one template for the programs. And there is basically a forgetful map from the template for the proofs to template for the programs. And because the inference rules are kind of syntax directed, there is a map between the 2 interpretations, and the soundness theorem of the logic is expressed as properties of this map. And now I'm just going to give a taste of how we interpret the proofs and the programs, which kind of objects we use. Basically, we use transition systems, which are a graph, direct graph with nodes and transitions between them, and two subsets, one of the initial nodes and one of the final nodes. And the natural way of representing it that we use is as a cospan in the category of graphs. So here C is basically the whole graph, and here's the input and the output nodes. And now basically each node needs to be associated with some states. And for that we use the templates, which are just kind of labeling graphs. There are 2 kinds, with 0 for the objects, for the interfaces, and 1 for the support. And so here, right, this lower cospan is what we call templates, and the whole thing is what we call cobordisms. And that's basically we interpret proofs and programs as cobordisms. That's it.
Okay, thanks very much. So are there any questions in the room?
Yes, I have a small question.
Yes, please go ahead.
So I think I remember that in order to interpret, or was it sequential composition maybe? You had cospans which had different ends. So you had to do a trick to relate them. Can you elaborate on that, please? Yeah, something like that. Yeah.
So basically, for example, in this example, right, the kind of output interface has kind of 2 copies of states, right? But here there's only 1 copy. But we still want to be able to compose sequentially any 2 programs, right? Because it's untyped. And basically we kind of put in the middle some gadget, which looks like this. And the important thing is that this gadget doesn't contain any transition. In the concurrent setting, no code transition. So that when we compose the 3 cobordisms, basically we identify every state, every node of the output of C1, C2, and the input of D, which have the same underlying memory state. Right. So that basically, when at the end of the program, we forget which path we took to arrive to the given memory state. I don't know if it helps.
It does a bit, but then the feeling isn't always the same, right? It depends on the ends of the considered cospans.
Yes. So like
yes.
Well, maybe I can.
Basically, you just map any node here to its underlying state, right? And then every node here to its underlying state. So then when you do the composition, you identify everything.
Maybe I can say a word. I think it's really, I mean, the example is very clear here. I mean, you have a choice, yes? If you want to do if B, then C1, L, C2, there's a branch, okay, between C1 and C2. and then you need to do something about the output of C1 and C2. So one way is to keep it like this without any, I mean, just say, okay, I have C1 and C2, but then D would need to be probably duplicated. Yes. So I mean, if you really want to say something, you could say it looks like a additive box. Okay, maybe if you want to speak about linear logic. So it's a way to glue C1 and C2, although only, of course, one of them has been, executed. I mean, one of the branches has been executed only. And so we needed to develop indeed the theory of, how we glue things in such a way that we can use always the same states as output for our programs or for our proofs, okay? Because one strength of the paper is that we really have a completely uniform way to interpret proofs and to interpret programs, and the only difference is the template we use.
Thanks. So there is a question from Slack, which is what program constructs can you interpret and which you can't? So it's a very open question, open-ended question.
Sure.
But yes, do you have something to say about that?
I mean, so like what we can do, basically,
Yeah,
sequential and parallel composition, right? So then branches and whatnot are kind of included in that. But the main thing we cannot do is higher order.
But this, I don't entirely understand why you cannot do higher order with that. Can you elaborate on that?
I mean, it's not that we cannot do it, it's that we don't do it in the paper.
Yes, you don't do it in the paper, right? I mean, the control flow is quite, it goes forward in time. But there is nothing that prevents you from using that to model higher order.
It's still, I mean, it's still a question how to do it properly. Yes, neatly. But of course, I think we believe with Leo we can do it. The nice thing and a quite amusing thing is that the framework we use is very similar to the framework I use for template games for linear logic, so which are higher order. But
Yes.
there are interesting differences in the way things are. So I think really it's a very nice combination of ideas between linear logic and separation logic, so that we can see the differences between the two languages, and in particular, the notion of interface. So here, something that Leo mentioned is we have the sequential composition. So we glue two programs like you see on the picture, one after the other. So the interface is time, before, after. But there is also the parallel composition where the interface is really more like game semantics.
Yes.
And here what we do is we have interface through a state, so shared, with LICS, so shared states with LICS, and it's different from the kind of interaction we have between games. But the beauty is that we see in the templates the differences. So really so I think when Leo said we can't, it means here using these templates. But the question is how we can extend the templates, and so. We're thinking a lot with Leo about that and how to, in a way. But the purpose is not to, just get there and interpret things. It's also each time to understand how the templates are describing the situation. So we really believe that this old idea coming, from Milner about concurrency, that it's good to have some kind of labeling, algebra of labeling is important, and in a way, we're just going in that direction, mixing it with new ideas.
Thank you very much. It's actually, I have many questions about this piece of work. I am very interested. I would be glad to talk more about, well, maybe if there is one last question from the room, we can have one more question on this.
I guess there is still this question from Andrea Turini on Slack, the last one, which I also posted in the Zoom chat.
It's also a very open-ended question. So it says the definition of the double category COB of cobordisms in slides 9 and 10 is not so easy to understand for those who have no relevant previous knowledge. Could you give a brief explanation about some properties, significance, and motivation of COB? I feel like it's going to be a hard one to answer in
Yeah,
in a
you
few
can
minutes.
also answer more of these questions in the Slack channel later, but perhaps you can just give a brief explanation here.
You?
Yes. Well, I mean, the significance, I mean, so like it's always useful to have like a setting where you can interpret things. I mean, to organize the thing, right? So like the object we really care about here is the cobordisms, which are horizontal morphisms in our double category. And basically, thanks to that, right, you can define, so here the double cells, which are basically a map of cobordisms. And basically, it's just a graph homomorphism between this cobordism and this one. And it's kind of some kind of simulation, right? And I don't know. I mean, it's like, yeah. I mean, the definition is kind of the only one you can give. And then you can express properties saying that, so like, for example, for composition, you can say that it is a double category, which means that sequential composition has good properties. And then for the parallel product, we can say that it's basically a monoidal product. So
yeah, maybe something we can say is that, I mean, you're always welcome to email us, and we're happy to.
You can also answer questions in Slack. So that's going to be online for a bit of time, I think, so you can have a more in-depth discussion.
Yes, and this notion of cobordism is not our invention. It's coming from, there is a long literature. Then the question is how to label it, how to organize and integrate it with concurrent separation logic, and this is really the purpose of the work. But the very notion of cobordism is and the way it's described here by push-outs is something people have explored for the past 15 years, actually.
Okay, thank you very much for these answers. I think now it's time to go on to the next speaker. And so the next speaker is Ross Horn, the talk being about logic beyond formulas. Ross, your microphone is muted.
Yeah, so once you've shared the screen, getting the microphone on.
Good, excellent.
So I just shared a whiteboard so we can be interactive here. So any questions during the talk are welcome. So our paper is, in short, Logic Beyond Formulas, and there's three authors. There's Matteo, who's here, Lutz, who's on a beach somewhere just now on the phone, and myself. This actually stemmed from a really simple observation. I thought this was too simple. So you want to model a queue in logic, and what we do is we say, we want to model a queue. We have the enqueue events here. Use another marker here. And say we want to enqueue A, we need to dequeue A. And we have to dequeue A after we enqueue A, okay? So that's where all of these are coming from. And then, because it's a queue, we want to order things as they come in. So if we enqueue A before we enqueue B, then we must dequeue them in the same order. And this, when you try and model this kind of structure, already you get this N shape. You see this N shape in the middle of this slide. And that means we can't actually write down a formula in terms of binary operators to represent it. And we tried to identify the essence of this problem if we want to do a logic for reasoning about these structures. And we were able to identify it. It boiled down to, you can capture it in the symmetric operators, which are available just for modeling and or. So if we want to write, for instance, A and B and C and D like this, we can model this as a graph. So we put an edge wherever there's an AND operator, and where there's an OR operator, we don't write any edge in the middle. Okay. And yet, if we want to do a very simple extension in the graphical plane, where we just add this edge in between, we get this N shape here. Then again, we can't write down any formula, but maybe we want to do some logic about it. We've got some applications for this. So, but when we want to design a logic, then it comes to the question of what, I mean, there's no semantics, there's no precedent for a logic which works over these structures. So we ask some fundamental questions, like for instance, is this implication at the top, this N, implying the other structure that you saw, is this a valid implication? And the answer is, no, it cannot be a valid implication, otherwise the logic is inconsistent, for instance. So you can actually argue this from fundamental logical principles. And again, from logical principles, we were able to say that, for instance, this shape here does, though, however, imply the N. And once we have figured out from logical principles what should hold and what should not hold, so these are kind of lower and upper bounds on what a logic can be over these things, we can design a proof system and we can start actually crunching these things. So if I want to prove that last statement, here's an example of a proof. So we have basically when we want to do an implication, we do the usual trick where we say not A or B is the same as A implies B. So what we do is we negate that structure we saw on the left. So this is a negation of what you saw before. And all that's happened is, notice the C has moved inside the structure here. Okay. And so it's now inside this N shape. And when you have two things together, what do you know? Not C or C, of course, they cancel each other out. So you can see it's disappeared at the top. And then we end up with something which corresponds to a formula which we can actually prove. So we know that this is provable. So this is the basic idea with our proof system, which we've designed. So we end up with this analytical propositional proof system, which works directly over graphs rather than formulas. Okay, and it's analytic and propositional proof system means that we have that analytic means that every conclusion has finitely many premises. And we can say it's propositional in the kind of the traditional Cook sense, because every rule can be checked in polynomial time still. And it's consistent. And essentially, a lot of this comes from proving cut elimination, which is the main contribution of our system. And the surprise was that in order to achieve cut elimination, we needed to generalize deep inference itself in order to achieve this. And if I have enough time, yes, I do, I can explain this little example of somewhere where a bit of deep inference is going on. It's a mini example. But what's happening here is we have basically this is a disjunction of three things. There's a not A, not B, and an N shape, okay? And the A, in order to prove the structure, what I do is that I have to move the A, not A inside next to the A, and then I have to move the B inside next to the B, and they cancel each other out. So that these will all end up being canceled out after that move. And we end up with not C or C, which of course is something we can prove. So we can actually prove these structures, and logical principles would also say that we need to be able to prove these kind of things. Okay, and here we go. So you talked about the proof system, but here is the proof system itself. There are three rules. There's this atomic interaction rule. This is just absolutely standard rule you find in almost any logic, which is if you have not A or A, then they can cancel each other out. Okay, and these contexts here on the outside is essentially this the fact that we can do anything in any context. Okay, we have this rule here, which is basically a generalization of the switch rule, which is at the core of multiplicative linear logic. And what it says is if we have some graph and we have some other graph that has a hole in it, so that's this thing is a hole here, then I can move G inside the hole here, as long as there was no edges in between. Notice there's nothing in here. There's no edges in between these two graphs. I'm always allowed to do this. I'm allowed to move things inside a context. And we have one other rule. This is required to get the cut elimination working, and some very, very basic principles such as reflexivity of implication. We have these prime rules, okay? And what is going on here is for every prime graph, these are graphs which can't be, don't have any kind of modules, which are these, modules are basically what we're using to represent contexts in the graphical settings as a generalization of context. So if we can't break them down using and or operators like this N shape, if we dualize it, we get the Z shape, you agree. So we take everywhere there was an edge, we add an edge, okay? And the prime rule says if you have these pairs of prime graphs, what you can do is you can take the corresponding components together and you can bring them together in the context with each other. So these are each coming from the corresponding parts of the graph and the prime graph. And then we have the complete graph, which relates all of these modules together. And we have one of these rules for every prime graph there exists. So there's infinitely many of them. And this is our graphical system GS, which we've come up with. So
yeah, I think you're on mute, right? Are you not?
Sorry about that. Yes, I was saying, sorry, we have a little bit of time left for question, but maybe we can start if there is any question from the room.
I can ask a very quick question. So in your slides and in your presentation also, you note that, for example, 3 buffer systems are something that you can't reason using formulas, but benefits from this graphical approach. Do you know anything in practice of something that people wanted to model that they just could not model symbolically because of the limitations of formulas?
So there's been a couple of talks in separation logic, so maybe we can talk about separation. Just to connect with the two. So in this separation logic, what do? You want to say that you have 2 spaces of things, and everything on one side is separated from everything on the other side, okay? And you model this using this binary operator. But there are patterns of separation which you cannot model if you just use binary operators to model. So there could be an application, for instance, for generalizing separation logic to allow patterns where you have more rich topologies, essentially, of separation in a system. This is one of our key motivations for this.
Thank you. So there is a question from Slack, which I'm going to read. So your work is amazing, and I would like to have a clarification about it. Since you use the notation of linear logic and you mentioned that the semantics is left as future work, I am curious about the possible differences between the semantics for your logic and the one for linear logic. Can you comment on this?
Yeah, so Matteo is going to respond to that one.
So we are currently looking at to extend the syntax of proofnet by Retore, the so-called Anson proofnet, which are based on co-graphs with perfect matching. Here we are taking into analysis to consider general graph with perfect matching. And once we have a correctness criterion, we can think that let's say the proofnet syntax can be semantics. So what we expect is that we have a generalization of multiplicative linear logic, of course, with mix. And to have an intuition in the semantic, we expect to have something which should look like some kind of generalized connective. For example, here the N and the Z should be 2 dual generalized connective on 4 on 4 elements. Okay. And so the idea that Ross was telling to have more general constructor we expect to find in the semantics of the system.
Okay, thank you.
I can also add just one brief thing is that we started off by taking semantics of linear logic and dropping the N condition, and it never works. So we do need something richer in order to capture this extra structure. This is interesting.
Okay. Thanks very much. I think we should go on to the next paper. I mean, this feels awfully short, but I think if we want to finish more or less on time, we should really go on. So thanks very much for these answers. So the next talk is by Alessio Monsuti about modal logics with composition on finite forests, expressivity and complexity.
Yes, I'm here. Can
we cannot hear you now. Okay, we can see your screen.
And now can you hear me?
Ah, yes, we can hear you, yes. So, yeah, please go ahead.
Okay, I don't know. Okay, so I hope there is not so much. Okay, no. Okay, so in this paper, we basically compare the composition operator from ambient logic and the composition operator for separation logic in terms of expressive power and complexity. And to do that, we introduced two modal logics, extending the standard modal logic with the two operators, the composition from ambient logic and the star from separation logic. So what we found is that when we consider the composition operator from ambient logic, the modal logic will become as expressive as graded modal logic, but its complexity, instead of being p-space complete, it will be alternating exponential time with polynomial many alternation. This is for the satisfiability problem. Instead, if we look at modal logic with the star operator of separation logic, the complexity is way higher. Instead of being elementary, is non-elementary. More precisely, is tower complete. But its expressive power is actually lower. It is strictly expressive antithesis between the complexity and expressive power of the two logics. And by using this framework of modal logic enriched with the composition from ambient logic and separation logic, what we managed to do is to solve some open problem on both logic regarding the complexity and expressive power of these logics. So to be quick.
Okay, thanks very much. Are there any questions from the room?
Yes, I posted one.
Yes. Okay, well, I will try to 1 second replug this because I cannot hear really well. Okay, can you hear me?
Yes.
Okay. Oh, that's
There's
better.
no echo also now. So.
Yeah, because yes, yeah.
So if there are no questions from the room, I can ask the question from Slack, which is the following. So I found your work where you compare the ambient and separation logics in terms of complexity and expressive power. Really interesting. Thanks. It is a very interesting topic, and you provided several diagrams to make the presentation easy to understand. I have, however, still some doubts about them. What is the exact meaning of the diagram in slide 9? And what do the differently colored squares represent? Okay, there are several questions.
Yes, let me pick the slides 1 second. So in slide 9, okay, so it's a little bit maybe I will try to be short as an answer, but so what I meant by this is, okay, you have let's say a model which will be, let's say, a tree. You have the current node for modal logic, which is W, and you will have a set of children that they will have also some trees. And now what we show is that actually graded modal logic is closed under a certain operator, which removes descendants that are not children. So here is a, let's say, a standard simulation proof. What you do is that you will use this operator on the left structure. And here this different color means that now I lost some descendant in the tree. And now the children will start satisfying different formulas. So for example, the children that are in yellow here, they will satisfy a certain set of formula, and the children that are in blue, another set of formula. And now you show that you can cut the other structure in a similar way, such that then you will preserve some invariant that will give you that the two models are still G by similar or undistinguishable with respect to graded modal logic. And so you prove this closure property. So, so it is, let's say, a little bit of a standard technique to show closure under a certain operator, and of course you can extend it to other operator if you want to.
Okay, thanks. Thanks for the answer. So are there questions from the room now? Okay, so then I'll ask a maybe slightly naive question, but I'm used to a semantics of the separating conjunction in separation logic, where you ask that, okay, so it applies on a heap, and if you have a separating conjunction, then the domains of the two subheaps should be disjoint. But that doesn't seem to be that condition in your semantics on trees. So can you elaborate on that?
So actually, I mean, let me just try to. Okay, so if you think a little bit of a heap and you stick with acyclic heaps, if you revert the edges, you get forests. So now the disjointness that you see in the domain of the heap is just that when I split the forest, the arrows will be in the two separated pieces. So it's really just, in a sense, the same condition, just that the models are slightly different. But from a computational point of view, heaps and forest behave really similarly because, I mean, for example, if you look at second order logic, I mean, you have Rabin theorem that it works on trees and unary function symbol. So it's really similar.
Okay, yes, thank you. Any other question?
Well, and just to compare, I mean, how do you interpret the separation tensor?
So the separation is interpreted just that you have your, this was the other one, sorry. The separation is just that you pick your forest and you assign two colors from the edges, and then the edges in one color will be one model, and the other color will be, which is exactly like, let's say in separation logic, you have the arrow of the heap and you put some arrow in one side and some arrow in the other side.
Your point is that depending on the separation, I mean the two different interpretations,
yes,
one is stronger than the other. Yes, so this is your result. And so you can interpret this one using the other one. Yes, this is your...
No, this would be the interpretation for the separation, yes. And you mean from heaps, with respect to the separation from heaps, or with respect to ambient logic, sorry.
Yeah. I mean, this is the result, yeah, isn't it? That one is a stronger logic than the other.
Yeah, yes. So actually, so for ambient logic, what will happen is that you have another condition. So what happens is that when you satisfy a formula, for example, phi chop psi from the ambient logic, it entails phi star psi from separation logic, but not vice versa. So the actual equivalence is a little bit different. You cannot really interpret one in the other. And what you have is that the star from separation logic corresponds from first applying this operator that we removed from descendant, and then use the chop from ambient logic.
Yeah, okay, this is what I had in mind. Yes, thank you. But
Yes.
then you have the star, but okay, I understand.
Okay.
Any other question? Okay, so maybe I have one other question, which is so one result is that ML chop has the same expressivity as graded modal logic, but has a very different complexity.
Yes.
So does that entail something on the size of formulas as well? So you know that maybe.
Yes. So you can always translate a formula from ML chop in an equivalent formula from graded modal logic that has exponential sides.
But are there formulas of ML chop for which you can, I don't know, you can prove that there is no formula of graded modal logic that is smaller than with an exponential lower?
Yes, you can. For instance, what you can say in ML chop is that I don't know, for example, fix a certain set of propositional symbol P1, Pn. You can say that you witness exactly one child for every possible combination of this P1, Pn. So it will be a model with exponentially many children. And this you will do it with a formula that is polynomial. And doing that in GML requires enumerating essentially all the possible combinations.
Okay, thank you. Okay, so perhaps we can, so thanks very much for these answers. And perhaps we can jump to the last talk of the session. And the speaker is Vedanta Ramanayak. I don't know, I'm not sure I'm pronouncing that right.
It's great.
Thanks. And so it's about extended Kripke lemma and decidability for hypersequent substructural logics.
Thanks. Okay. I guess everyone has the, yep, you can see my slides.
Yep.
Okay, great. Yeah, okay, so this is a result about a general decidability result on substructural logics. So in particular, if you know the full lembic calculus, this is about the commutative, associative, full lembic calculus with contraction. Alternatively, you could say intuitionistic, multiplicative, additive, linear logic with the contraction rule. And every extension of that logic that has a hypersequent calculus with analyticity, with the subformula property, we establish decidability here. So this covers infinitely many extensions, in particular, all possible finite combinations of familiar properties like you see on the screen with linearity, weak excluded middle, bounded width, and so on. The full lembic logic and its extensions in that vicinity find a lot of applications in many areas in computer science, for example, as listed there in formal languages, computational linguistics. You see substructural logics coming in of this nature in separation logic, computational resource modeling more generally, fuzzy logics, FLEC as a relevant logic, for example. And what you see is that emerging applications fuel the need for new extensions, and this is what really drives interest in general decidability results, like we present here. Okay, great. Here's maybe a picture to show the logics that we are considering here. So in red are the logics that we get some sort of pictorial representation of the logics that we have decidability. As you can see, it's extensions of FLEC with various properties and combinations. And the H that I put next to it denotes that these are the logics that have a hypersequent calculus with the subformula property. So if you're not exactly sure what that is, you might know the sequent calculus, which is what Gensen introduced and which was used since the 1930s. And Kripke showed decidability famously of FLEC using the sequent calculus. And if you consider Kripke's argument, what he did is he took the sequent calculus for FLEC, he took Curry's lemma, which I'll explain briefly, and then another lemma, which is later called Kripke's lemma, and he puts these ingredients in and he gets decidability of FLEC, that logic. But the sequent from a structural proof theory sense, the sequent calculus does not give you analyticity or subformula property for all these other logics that you want to consider. That's where the hypersequent calculus comes in, which can be seen as a multiset of sequence. And once you use the hypersequent calculus, you get analyticity or nice proof calculi for lots of logics. And now you need to see how you can extend what Kripke does there. And in this case, a significant extension is needed, both of the Curry's lemma to what I call the hypersequent Curry lemma, which shows a structural proof theoretic property of admissibility of contraction, and also an extended Kripke lemma where you need to bound your proof search. You say that, well, if you've got a sequence of hypersequence, well, at some point you're going to have this, it is a well quasi order. So at some point you can use the hypersequent Curry lemma to cut off the proof search, to terminate the proof search. And if you compare the Kripke's lemma, it's well known to be a reformulation of Dixon's lemma, which is exploiting that the usual ordering on n-tuples is a well quasi order. And what we need here is that a particular ordering that I subsequently found appears in the literature as the Meinering ordering or the Schmidt ordering, which is it's using the fact that on sets of n-tuples that it is a WPO, a well quasi order, and that's a deeper property in a formal sense as well. Thank you.
Thanks very much. So there are questions from the room. Okay, so I can start by asking a question. So, so this proves decidability for a bunch of different hypersequent calculi. But what is the, so is there a, I mean, what is the exact statement? So it's like you start, so it's hypersequent calculi for, well, can you say what?
Sure. So what happens is that FLEC has a sequent calculus with subformula property. Yes. And there are a lot of properties and axioms that you want to extend FLEC with. But the moment you add these properties to the sequent calculus, you no longer have the subformula property. What happens is that if you use a more expressive proof calculus called a hypersequent calculus,
Yes,
you can actually obtain calculi with proof calculi with the subformula property for all these infinitely many logics.
But what I'm not seeing from this statement is what is exactly the formal setting that you're considering. So you say covers infinitely many extensions, but
so you're referring
you start
to
with the hypersequent calculus for the full lambda logic with contraction and erasing. Is that no? What is the E? I don't. No, it's exchange. Okay.
Yeah, that's right. So E is exchange. That's right. It's this commutative associative
yes.
Thing with contraction rule. So
yeah.
in fact, there is a syntactic characterization of the logics that are being covered in this theorem. There's also a semantic characterization, for example, in terms of the algebraic semantics, which I have not put on the screen here. But yeah, so what is already understood is what logics you can cover by going from the sequent calculus to the hypersequent calculus, but that's already from 2008. The problem was that when you go to the hypersequent systems, they become very hard to control. So you cannot, for example, if you want to control the proof search, you just get a blow up because simply by going from sequence to the multisets or the sets of sequence.
Yes.
So what we show in this paper is how to get a handle on controlling this jump from sequence to sets of sequence, and it's compared from the order theoretic sense. It's going from n tuples to sets of n tuples, which is a deeper property. You need that it's sort of a omega squared well quasi order as opposed to a omega well quasi order.
Okay. Is there any question? Yes, there is a question from Lutz, I think.
Yes. So if I understand correctly, you generalize Kripke result from sequence to hypersequence. And my question is, do you see any way to generalize this also to logics with modalities present? Do you see any result for any kinds of modal logics?
So you mean modal logics where we need a hypersequent calculus, right?
No, any modal logic. I just sequent calculus with modalities. I mean, start basic. Just modalities present.
Oh, okay. So there are two ingredients here, right? So one, if you take what Kripke does, he observes how to prevent the proof search in the sequent calculus from he forces finiteness by observing some substructural property, right? That even though you have a contraction rule, at some point you're forced to repeat yourself, roughly speaking, right? So if you take a sequent calculus with the modal property, you'd want to go substructural to make it interesting. And yes, then it is possible already that if you can find an interesting sequent calculus with subformula property where the decidability is open, yes, a modal logic with a substructural basis. It's sure, but often a sequent calculus is very limited in its expressivity, right? So if you consider the hypersequent calculus level, you take this argument and you add modalities. Once again, yes, it's feasible that you will find some interesting modal logics where you can look for decidability, though I didn't consider modal substructural logics.
I mean, it would be already interesting to make a step back and look at the modal logics which are decidable and see whether that method could be applied to them. Right? I mean, that's maybe the thing that one should try first, instead of going immediately to the ones where decidable is not yet known.
Yeah, so one thing I draw your attention to is using this Dixon's lemma or Kripke's lemma, even for the sequent calculus. If you look at the bounds, so Urquhart in '99 got some tight bounds. So it's not primitive recursive, FLEC, but it is primitive recursive if you use the Ackermann function, right? So that's horrendous bounds somehow, right? So I guess you'd want to, so clearly the modal logics that you target would be ones that you suspect are decidable, but which have very bad complexity, right?
Okay, thank you. So, yeah, okay. Is there, maybe we can have one last question? Okay, so I'll ask one last question then. So, do systems for which you prove decidability, those are cut-free hypersequent systems, right?
Yes.
And so do all the, I mean, they all have cut elimination results?
Yes, they do. They do. So I'm coming into this problem using the hypersequent systems, which have cut elimination and subsequently also subformula property.
Yes.
The problem is when you're using multi-sets of sequence. In fact, initially looking at this problem, it's not clear that even though you have the subformula property, that it buys you anything, because there's a lot of degrees of freedom in which hypersequence can increase.
Yes.
So that's what's being controlled here.
Yes. Okay. Yes. Thank you.
Thank you.
So I think we are getting to the end of this first question-answer session. So thanks very much to the speakers and to the participants for coming. So I think now there is a break, and then the program starts again at 3:30 with an invited talk. Which is like there is nothing in the LICS program, is there? Okay.
Thank you very much, Pierre.
Thank you.